everyone. So now we're going to dive into the section in 11.3 in Thomson. It's the V minus A structure of the weak interaction, and we're going to understand what V minus A means, hopefully by the end of this section. So in the previous section, we saw that the weak interaction violates parity. In fact, it does this thing called violates it maximally, as there's actually no middle ground, it seems like. And what we're going to do is we're going to use these gamma 5 matrices to represent the axial vector part of the interaction. So this V here means the vector, and then the A means axial vector. Okay. Remember that vector has parity, right? So when you flip it, it does 180 degrees, and then everything just get reversed. Where axial vector does not flip when you do parity, right? So so it's the product of two vectors. So for example, angular momentum, right, is r cross p. There's two vectors cross product together to make a new vector, and that vector actually does not change when you do a parity operation on it, because right, the two vectors already has a negative, right? And when you multiply a negative to a negative, you get a positive. All right, so just to remind everyone, what is this gamma 5 matrices that we did in chapter 6, right? The gamma 5 matrix is actually the product of the other four gamma matrices, and then if you multiply this out in the direct representation, it will be the direct Pauli representation. You'll get these 4x4 matrix instead. So it's basically a identity matrix, but it's off the diagonal instead. Okay. These gamma 5 matrices obey the same commutation relations as the other gamma matrices, where if you square them, you get 1. They are Hermitian, so the dagger of self is self, and they anti-commute with each other, right? Where if you switch the order, you get a negative sign instead. Okay. So let's see how these gamma 5 matrices come into play when we're dealing with the weak interaction. Okay. Okay. So in QED and QCD, right, the interaction is through these things called vector bosons. These are the photons and the gluon. And then when we're writing the Feynman rule, so let's say we have a vertex vector here, right? Let's say we have maybe an electron scattering off something. We don't actually know, it doesn't actually matter what it is, right? When we write the Feynman rules, right, we start backward here. So we use, let's say this is P3, P1. We write that the spinner of P3, right? And then we get to the vertex part. This vertex vector, right, is always proportional to gamma mu. And then now you're in the incoming particle, which is represented by U of P1. Okay. So that's the current, right, where it follows the flow of this electron from the incoming to the outgoing. Okay. Right. And this is actually known as a vector coupling current, where we're going to represent this as, this is actually just J mu in general, right? For this case, the electron. Okay. And what we're going to do is we're actually going to denote this with the capital V on the bottom to denote that this is actually a vector coupling, okay, for the photon and the gluon. Okay. And this is, basically a copy of this where you have U and then you have this gamma mu, and then you have the incoming whatever electron fermion that's coming in. Okay. This is actually known as a bilinear covariant current. Don't worry about memorizing these names. It's just a mathematical terms. But the reasons for introducing this is that there are other types of currents that we haven't dealt with. Namely, the one we're going to deal with now is actually the axial vector, hence the V minus A. So we're going to have a V minus A version of this. Okay. So the weak interaction is actually both a vector and an axial vector interaction. Okay. In fact, if you were to try to write the Feynman rules for a weak interaction vertex, so let's say you have an electron coming in and it spits out, this is going to be a W minus, and then this turns into a neutrino. Okay, what's going to happen is that this vertex factor here, instead of just being gamma mu, okay, it's going to have some vector piece of it, gamma mu, and some axial vector part of it, gamma mu times gamma 5. Okay, so the gamma 5 represents the axial part, and these constant GA, GV, and GA represent how much vector and how much axial vectors are there in each of the pieces. In fact, what you can do is actually simplify this by just factoring these, multiplying these through. You can write that there's some vector current and then there's some axial vector current piece, okay? And how big they are is represented by this GV and GA, okay? In general, GV and GA can be any number, right? You know, GA can be very big or GV can be very big, and then vice versa, and then these two get balanced to itself. But what we observe experimentally is that the weak interaction has exactly V minus A, where there's actually the equal parts on each, but there's a subtraction between them instead. So what happens is that, so when we're writing the weak interaction current, what you actually have is something that's proportional. In fact, what I'm going to do is going to remove this proportionality sign, okay? And we're going to write that this is proportional. Well, I'll fill in the GW later, okay? Okay, I guess that's why he writes the proportional sign. Proportional to, right, something that's U of, you know, P outgoing, right? And then, right, I'm going to put a 1 here for GV, okay? And then this will give you a gamma mu. And then if GA is minus 1, then you get a minus 1 here. You get a gamma mu here, you get a gamma 5, right? And then you have the incoming particle. Okay, so up here, right, this will be P, this will be P prime. Okay, now I'm going to modify this a little bit, right? So this proportionality, okay, we're going to have basically the weak coupling constant to be proportional to it. Okay, in order to deal with both of these, what we're going to have a square root of 2 underneath here. Okay. All right. So, well, now, right, if we were to do the Feynman rules for the weak interactions, which is what I'm going to do down here, right? So we have a electron coming in, electron. Let's say this is a neutrino, and then it spits out a W boson, right? What I'm going to do is that this is P prime, P. Okay, the way I'm going to write this vertex is that I'm going to have, well, this is a neutrino, so it's a particle, so this will be whatever U of P prime. Go over here. Okay. Oh, yeah, in fact, because there's 2 gamma matrices here, I'm going to do this actually a factor of 2 down here also, just so they normalize to 1. Okay. All right. And I'm going to write, let's just follow the Feynman rules, right? So instead of the regular vertex, the QED vertex, we're going to replace it with this vertex, okay, minus GW, 1 over square root of 2. There's a minus I in front, just to make everything Hermitian, okay, gamma mu, okay, and 1 minus gamma 5, okay, and then I'm going to write the incoming electron momentum spinner, okay. So when you multiply this out, right, you get minus I G omega GW, right? This is just a number, so you can factor this out for 2, okay? And then you have U bar P prime, right? And this is gonna, if I multiply this in, I'm gonna get gamma mu here, minus gamma 5, gamma mu, and then you have UP over here. Okay, and that's exactly what we have up here. Okay, modulus these factors that is justified by because you have two gamma matrices here, so they have to be renormalized to basically square root of 2. And this additional 1/2, I think, is just a chosen so that we have a different number of polarization in the W boson. So that's how the weak interaction is different from the electrodynamics and the chromodynamics because the weak interaction follows this V minus A thing. And essentially, mathematically, the standard model could be anything, and it just happened that both of these factors in front of the V and the A is actually 1 and -1. Okay, and this is the statement where because both the vector and the axial vector part of the interaction contributes equally, but then in opposite directions. Okay, this is one of the saying that the weak interaction actually violates parity maximally, meaning it's actually not possible, for example, to have a certain handedness in neutrino, and we're going to see that in the next chapter.